Lab 3 deals with the analysis of the motion of a star orbiting around a black hole. We're given the initial position of the black hole, the mass of the star, the change in time between data points, and the position data. The trajectory of the star is unique to each person based upon the input characters of his or her email address. The ultimate goal of the lab is to determine the mass of the black hole. However, in order to achieve this quantity, we must first find the net force on the star. We can operate under the assumption that the only forces experienced by the star are due to the black hole. Using this information, I obtain the mass of the black hole to be 1.35285 times 10 to the 35 kilograms. We're starting with the knowledge of the motion of the star, and we're using that information to calculate motion quantities. This is the opposite of the process used in the two previous labs, in which the initial conditions were given with the intention of finding out about the future motion of the object. In this lab, we use the fundamental momentum principle to find Fnet. Now let's take a look at the code in VPython. First, I inserted a few initial conditions. I created a black hole for visualization purposes. I also assigned the value of g, the universal gravitational constant. I input the mass of the star and the initial position of the black hole, as given in the lab introduction. Delta t, or the time interval between data points, is 1 day, or 86,400 seconds. Then I found the x and y velocity by utilizing the indexing function of VPython. Essentially, I found the change in position for each set of x and y data points, and then I divided this by the change in time, or 1 day. The first part of the while loop calculates various motion data points, including the initial and final velocity, the initial and final momentum, the change in velocity, and the change in momentum. These data points are used to find dp dt, or the change in momentum. Then we find that Fnet equals dp dt. This is based on the momentum principle in Newton's second law. We can use this principle to find the parallel and perpendicular components of the force, and thus the parallel and perpendicular components of the change in momentum. The parallel component describes the change in speed of the star, while the perpendicular component describes the change in direction of the star. According to Newton's second law, the parallel component of the net force is equal to the parallel component of the change in momentum. The perpendicular component is found in a similar way, this time by subtracting the parallel component from the total net force. The remainder is the value of the perpendicular component of the net force, and thus the perpendicular component of the change in momentum. After finding the components of the net force, the next step to finding the mass of the black hole is to apply the universal gravitational principle. The standard equation for the universal gravitational principle is net force equals the universal gravitational constant times the mass of the star times the mass of the black hole divided by the distance between the two squared. I then solved for the mass of the black hole. As mentioned earlier, I obtained 1.35285 times 10 to the 35 kilograms. This is the result when I run the program. The path of the star around the black hole is elliptical, which allows for dramatic representations of the force component arrows. In the model, the red arrow is the perpendicular component. It is always perpendicular to the path of the star. It represents the change in direction of the star. The parallel component is represented by the blue arrow. As the star approaches the black hole, the force increases, so the magnitude of all the force arrows greatly increase. The parallel component, which indicates the change in speed, is the greatest as the star passes closest to the black hole. The green arrow represents the net force, which is also the greatest in magnitude when it is closest to the black hole. The net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components due to the momentum principle. The momentum principle essentially states that the total momentum in a system remains the same before and after any interaction. When you take the derivative of the velocity in the momentum principle statement, you obtain an equation for Newton's second law, force equals mass times acceleration. The net force and its parallel and perpendicular components are representative of the pushes and pulls on the system in different directions. On the other hand, the parallel components of the rate of change of momentum indicate a change in speed, and the perpendicular components of the rate of change of momentum indicate a change in direction. In this case, we use the motion calculations to find an expression for dp dt, and then we equate that to Fnet using an expression of the momentum principle. It is possible to find a value for the mass of the new black hole, but it will be the same as the mass calculated previously. Since the motion of the observed star remains unchanged, the components of the gravitational equation used to find the mass of the black hole will be the same. Since the mass and the position do not change, the net force and the relative distance do not change either. Therefore, you will not be able to tell a difference, assuming the trajectory of the star remains unchanged.